November 12, 2023, Virgin Atlantic Flight 100 prepares for departure at London's Heathrow Airport. Captain David Williams runs through his pre-flight checklist, completely unaware that he's about to make aviation history. The Boeing 787 Dreamliner behind him looks identical to thousands of others that cross the Atlantic every day. Same engines, same avionics, same passenger cabin, but there's something different about this aircraft that will change everything we thought we knew about flying. In the fuel tanks beneath his feet sit 70 tons of liquid that started its journey not in an oil field or refinery, but in the deep fryers of McDonald's restaurants across Europe. This isn't jet fuel as we've known it for 70 years. It's made from used cooking oil, the same greasy waste that most people scrape into trash cans without a second thought. What Captain Williams doesn't know is that his 8-hour flight to New York will prove that aviation's biggest problem has been hiding in plain sight behind every restaurant dumpster in the world. The numbers tell a devastating story. Aviation produces 2.5% of global carbon emissions, and that figure is set to triple in the next 20 years as air travel demand explodes. By 2039, the global aircraft fleet will nearly double from 25,900 planes to 49,405. Every single one of those aircraft burns fossil fuel that pumps carbon dioxide directly into the atmosphere at cruising altitude, where it does maximum damage to our climate. Airlines have tried everything: more efficient engines, lighter aircraft, optimized flight paths. Nothing moves the needle significantly because the fundamental problem remains unchanged. Commercial aviation runs on kerosene, a fossil fuel that releases carbon that's been locked underground for millions of years. But what if the solution isn't more technology or better engineering? What if it's something so simple, so obvious that we've been throwing it away every day for decades? The breakthrough didn't come from aerospace engineers or petroleum companies. It came from an observation so basic it sounds ridiculous. Every restaurant in the world produces gallons of used cooking oil daily. That oil contains the same energy-dense hydrocarbon chains that power jet engines. The only difference is where it comes from. Instead of drilling miles underground to extract ancient organic matter, why not use organic matter that's already circulating in our food system? The idea seems absurd until you understand the chemistry. Jet fuel is essentially long chains of carbon and hydrogen atoms packed with energy. Used cooking oil contains identical molecular structures. Both burn at similar temperatures, produce comparable energy output, and flow through aircraft fuel systems with identical characteristics. The difference isn't chemical, it's philosophical. One source adds new carbon to the atmosphere, the other recycles carbon that's already there. James Howell doesn't look like a climate hero. Every Tuesday afternoon, he backs his truck into the alley behind Le Diplomat restaurant in Washington, D.C., connects a rubber hose to the kitchen's waste oil container, and flips a switch. The hose slurps 200 gallons of used cooking oil into his gleaming steel tank with a loud drone that echoes off the brick walls. To most people walking past, he's just collecting restaurant waste. But Howell is actually gathering the raw material for aviation's future. The oil in his truck contains the molecular remnants of fried chicken, French fries, and countless other meals. It's dark, viscous, and smells like a combination of every fast food restaurant you've ever entered. This is what airlines are talking about when they discuss burning cleaner fuel: the contents of padlocked dumpsters behind Buffalo Wild Wings sports bars and thousands of other restaurants across the globe. After Howell finishes his collection route, he unloads at a processing depot where the oil undergoes its first transformation. Workers filter out water, flour, spices, and floating food particles. What emerges is still recognizably waste cooking oil, but cleaner and more consistent. This filtered oil then begins a journey that mirrors the global petroleum supply chain, except instead of crude oil moving from wells to refineries, used cooking oil travels from restaurants to fuel production facilities. Tanker ships arrive twice weekly at a massive refinery in Rotterdam operated by Neste, currently the world's largest producer of sustainable aviation fuel. The ships pump their greasy cargo into insulated holding tanks heated to 140 degrees Fahrenheit. The heat keeps the fats and oils liquid so they flow easily through miles of pipes that snake through the facility. What happens next is where kitchen waste becomes aviation fuel through a process that would make any chemist proud. The transformation requires sophisticated industrial equipment and precise chemical control. Neste uses specialized clay called bleaching earth to strip unwanted compounds from the oil. Sodium from salty foods, phosphorus from various ingredients, and trace metals all get filtered out. The remaining oil undergoes hydroprocessing, where hydrogen molecules are added under high pressure and temperature. Catalysts break down complex molecular structures and rebuild them into the specific hydrocarbon chains that jet engines require. The end result is HEFASPK, or hydroprocessed esters and fatty acids synthetic paraffinic kerosene. The technical name sounds intimidating, but the product is molecularly nearly identical to conventional jet fuel. It has the same energy density, the same freezing point, and the same combustion characteristics. The only significant difference is its origin story. Testing this revolutionary fuel required overcoming decades of aviation conservatism and regulatory caution. When Pratt & Whitney engineers first proposed running their V2500 engine on 100% sustainable aviation fuel, the reaction was predictable skepticism. Aviation operates on the principle that if it's not broken, don't fix it. Every component, every fluid, every procedure gets tested exhaustively because failure at 35,000 feet isn't an option. The V2500 engine test represented months of preparation and coordination. First, technicians established baseline performance by running the engine on conventional Jet A fuel. They measured thrust output, fuel consumption, combustion temperatures, and emissions across multiple power settings. Every parameter got recorded and analyzed. Then came the moment of truth. The fuel lines and tank were flushed completely clean, and the cooking oil-based fuel flowed into the system for the first time. The results surprised even the engineers who expected success. There were no surprises. The engine performed exactly as they knew it would. Thrust output remained consistent across all power settings. Fuel consumption stayed within normal parameters. Combustion characteristics showed no anomalies. If anything, the sustainable fuel burned slightly cleaner than conventional kerosene, producing fewer particulate emissions and aromatic compounds. This wasn't the first engine Pratt & Whitney had tested on sustainable aviation fuel. By the time they evaluated the V2500, they had already validated 8 other engine models on 100% SAF. Each test built confidence that cooking oil-based fuel could serve as a complete replacement for fossil jet fuel without requiring any modifications to existing aircraft or infrastructure. But engine testing in controlled laboratory conditions is one thing. Proving the fuel works on actual commercial flights covering thousands of miles is entirely different. That's where Virgin Atlantic's Flight 100 enters the story as the ultimate real-world validation. The regulatory approval process for Flight 100 took months of coordination between Virgin Atlantic, fuel suppliers, airport authorities, and aviation regulators. The UK's Civil Aviation Authority meticulously scrutinised every aspect of the planned flight. Safety assessments covered fuel quality standards, aircraft compatibility, crew training requirements, and emergency procedures. The regulatory framework for sustainable aviation fuel was still evolving, with most rules limiting SAF blends to 50% mixed with conventional fuel. Virgin Atlantic's request to operate a commercial flight on 100% sustainable aviation fuel required special permissions and extensive documentation. The airline had to prove that their fuel met all ASTM international standards for jet fuel quality. They submitted detailed analysis of the fuel's chemical composition, performance characteristics, and production process. Every batch of fuel got tested for contamination, energy content, freezing point, and dozens of other parameters. The flight crew received specialized briefing on the sustainable fuel. Though operationally nothing would be different from flying with conventional jet fuel, Captain Williams and his co-pilot studied fuel system procedures, emergency protocols, and performance calculations. The sustainable aviation fuel behaved identically to regular jet fuel in all aircraft systems, requiring no changes to standard operating procedures. On board Flight 100, notable passengers included Virgin founder Sir Richard Branson, UK Transport Secretary Mark Harper, and Virgin Atlantic CEO Shay Weiss. The passenger manifest read like a who's who of sustainable aviation advocates, but the real significance lay in what powered their journey across the Atlantic. Every gallon of fuel in their tanks had previously fried food in restaurants across Europe before being transformed into aviation fuel through advanced chemical processing. The 8-hour flight proceeded without incident. Engine performance remained within normal parameters throughout all phases of flight. Fuel consumption matched predictions based on conventional fuel calculations. The aircraft's range, payload capacity, and operational ceiling showed no degradation compared to fossil fuel operations. From the flight deck, Captain Williams reported that the sustainable fuel produced no noticeable differences in aircraft handling or engine behavior. But behind this successful demonstration lay a complex global supply chain that most passengers never see. The journey from restaurant fryer to aircraft fuel tank involves thousands of collection points, processing facilities, and transportation networks spanning multiple continents. Understanding this supply chain reveals both the enormous potential and significant challenges of scaling sustainable aviation fuel production to meet global demand. Used cooking oil collection operates like an invisible parallel economy. Companies like the one James Howell works for maintain regular pickup routes at restaurants, hotels, cafeterias, and food processing facilities. Drivers know exactly which establishments produce the highest quality waste oil and which locations generate contaminated batches unsuitable for fuel production. The economics have shifted dramatically as demand for waste cooking oil increased, turning what was once a disposal cost into a revenue stream for restaurants. Quality control begins at collection. Oil contaminated with water, cleaning chemicals, or excessive food particles gets rejected or sent to lower-grade applications. The best material flows towards sustainable aviation fuel production, while lesser quality oil might become biodiesel for trucks or heating oil for buildings. This sorting process ensures that only suitable feedstock reaches the sophisticated refineries capable of producing aviation-grade fuel. The global nature of this supply chain creates both opportunities and vulnerabilities. Cooking oil waste production doesn't align geographically with aviation fuel demand. European and North American restaurants generate significant waste oil volumes, but Asia-Pacific aviation markets are growing fastest. This mismatch requires international shipping of both raw waste oil and finished sustainable aviation fuel, adding complexity and cost to the supply chain. Transportation costs become significant when moving low-value waste materials across oceans. Specialized tanker vessels carry used cooking oil from collection regions to major refineries, following routes similar to crude oil shipments. The economics only work when refineries achieve sufficient scale to justify the transportation and processing costs involved in converting waste oil into premium aviation fuel. Storage and handling present unique challenges for used cooking oil compared to conventional petroleum products. The oil must be kept heated to remain liquid and prevent solidification in tanks and pipes. Contamination risks increase when different oil batches get mixed without proper quality control. Some waste oil arrives with water content, food particles, or chemical residues that complicate processing and reduce yield of finished fuel. Quality assurance becomes critical as economic incentives create potential for fraud in the supply chain. Rising Asian exports of used cooking oil have sparked investigations into fake UCO, with virgin palm oil being relabeled to capture subsidies intended for waste-based fuels. This requires sophisticated testing and chain-of-custody documentation to verify that shipments contain genuine waste oil rather than virgin vegetable oils diverted from food production. The transformation of waste cooking oil into jet fuel requires industrial facilities comparable to traditional petroleum refineries in scale and complexity. These plants represent hundreds of millions of dollars in capital investment, with sophisticated equipment for chemical processing, quality control, and environmental compliance. The technology exists and works reliably, but building sufficient production capacity to supply global aviation demand requires massive coordinated investment across the industry. The production capacity challenge becomes starkly apparent when you examine the numbers. Last year, airlines burned 340 million gallons of sustainable aviation fuel, nearly all of it made from used cooking oil or animal fat. That sounds impressive until you realize airlines consumed 114 billion gallons of fuel overall. The sustainable fuel represents less than 0.3% of total consumption. At current production rates, scaling to meet even 10% of aviation fuel demand would require a 3,000% increase in manufacturing capacity. Neste's Rotterdam facility represents the cutting edge of sustainable aviation fuel production, but even this massive operation can only produce 1.5 million tons annually by 2025. That's enough fuel for roughly 15,000 transatlantic flights per year, a fraction of the 100,000 flights that cross the Atlantic annually. Building equivalent facilities worldwide would require coordinated investment exceeding $250 billion, according to United Airlines CEO Scott Kirby. The mathematics of supply become even more challenging when you consider feedstock availability. The world simply doesn't produce enough used cooking oil to replace all aviation fuel. Global waste cooking oil generation totals approximately 30 million tons annually from the 10 largest producing countries. But this figure only accounts for established collection networks. Vast quantities of waste oil in developing countries never get collected, instead being dumped into sewers or landfills where it causes environmental damage. Even if collection efficiency improved dramatically, used cooking oil alone cannot meet aviation's fuel requirements. The industry burns fuel at a rate that would consume the world's entire waste oil supply in less than 6 months. This reality forces sustainable aviation fuel producers to explore alternative feedstocks while establishing the infrastructure and processes needed to handle diverse waste streams. Municipal waste emerges as a promising supplemental source. Household garbage contains organic matter that can be processed into aviation fuel through advanced chemical conversion. Agricultural residues from crop harvesting provide another potential feedstock, along with forestry waste from lumber operations. Animal fats from meat processing facilities offer high-quality material similar to used cooking oil in chemical composition. The diversity of potential feedstocks creates new challenges challenges for fuel producers. Each source requires different processing techniques, quality control procedures, and supply chain management approaches. A facility designed to handle used cooking oil cannot automatically process municipal waste or agricultural residues without significant modifications. This technical complexity increases capital costs and operational complexity for sustainable fuel production. Industrial off-gases represent an entirely different approach to sustainable aviation fuel production. Certain manufacturing processes release carbon-containing gases that can be captured and converted into jet fuel through synthetic chemistry. This pathway doesn't depend on biological feedstocks, but instead recycles carbon that would otherwise enter the atmosphere as waste emissions. Algae-based fuel production offers theoretical advantages in terms of yield per acre and minimal land use competition with food crops. Some algae species produce oil content exceeding 50% of their body weight, far higher than traditional crop-based sources. However, commercial algae fuel production remains expensive and energy-intensive, with most projects failing to achieve economic viability at industrial scale. The technical sophistication required for alternative feedstock processing pushes sustainable aviation fuel production beyond simple chemistry into advanced materials science and process engineering. Converting municipal waste into jet fuel requires pyrolysis systems operating at temperatures exceeding 800 degrees Celsius, followed by hydroprocessing under extreme pressure. The complexity rivals traditional petroleum refining, while dealing with far more variable and contaminated input materials. Quality control becomes exponentially more difficult when processing diverse waste streams. Used cooking oil from restaurants maintains relatively consistent chemical composition, but municipal waste varies dramatically in content and contamination levels. A single batch might contain plastics, metals, organic matter, and chemical residues that complicate processing and affect final fuel quality. Economic pressures drive innovation in feedstock utilization and processing efficiency. The current price differential between sustainable aviation fuel and conventional jet fuel creates powerful incentives for technological advancement. Sustainable fuel costs approximately 4 times more than fossil fuel, making airlines reluctant to adopt it without regulatory mandates or significant government subsidies. California's low-carbon fuel standard and the European Union's emissions trading system provide economic incentives that help bridge the price gap. These programs assign carbon credits to sustainable fuels based on their life cycle emissions reductions, creating additional revenue streams for producers. Waste-based feedstocks earn the highest credit values because they avoid the land use and food security concerns associated with crop-based alternatives. The regulatory landscape evolves rapidly as governments recognize aviation's environmental impact and set increasingly aggressive decarbonization targets. The European Union requires aviation fuel suppliers to provide minimum sustainable fuel percentages, starting at 2% in 2025 and reaching 70% by 2050. These mandates create market certainty that justifies the massive investments required for production capacity expansion. United States policy focuses more on tax incentives and research funding rather than direct mandates. The Inflation Reduction Act provides substantial tax credits for sustainable aviation fuel production, while the Department of Energy funds research into advanced conversion technologies. This approach allows market forces to drive adoption while providing financial support for early-stage development. International coordination becomes essential as aviation operates across national boundaries and requires consistent fuel standards globally. The International Civil Aviation Organization works to harmonize sustainable fuel specifications and certification processes, ensuring that fuel approved in one country meets safety standards worldwide. This coordination prevents the fragmentation that could complicate international flights and fuel supply chains. Engine manufacturers play a crucial role in validating sustainable fuels and building industry confidence in their safety and performance. Pratt & Whitney's extensive testing program demonstrates that multiple engine types can operate safely on 100% sustainable aviation fuel without modifications. This testing eliminates concerns about aircraft compatibility and provides airlines with confidence to invest in sustainable fuel adoption. The V2500 engine test that validated cooking oil-based fuel represents just one data point in a comprehensive evaluation program spanning years of development. Engineers subjected the fuel to extreme conditions that exceed normal flight operations, including high altitude, temperature variations, and emergency scenarios. Every test confirmed that sustainable aviation fuel performs identically to conventional kerosene across all operational parameters. Durability testing examines whether sustainable fuels cause long-term engine wear or component degradation. Extended operation on sustainable aviation fuel shows no increase in maintenance requirements or premature component failure. In some cases, the cleaner burning characteristics of sustainable fuel actually reduce engine wear and extend maintenance intervals compared to conventional fuel operation. Emissions testing reveals significant environmental benefits beyond carbon dioxide reduction. Sustainable aviation fuel produces fewer particulate matter emissions, lower sulfur compounds, and reduced aromatic hydrocarbons during combustion. These improvements enhance local air quality around airports and reduce the environmental impact of aviation operations on surrounding communities. The success of Flight 100 catalyzed industry interest in sustainable aviation fuel beyond what years of technical studies and regulatory discussions achieved. A single successful transatlantic flight demonstrated practical viability more convincingly than laboratory testing or computer modeling. Airlines that previously viewed sustainable fuel as a distant future consideration began requesting supply quotes and negotiating purchase agreements. Virgin Atlantic's achievement forced competitors to accelerate their own sustainable fuel initiatives. British Airways, Lufthansa, and Air France-KLM announced expanded sustainable fuel programs within months of Flight 100's completion. The demonstration effect created momentum that technical arguments alone had failed to generate, proving that sometimes showing works better than telling. The psychological impact of Flight 100 extended beyond the aviation industry to passengers, environmental groups, and policymakers. Seeing a commercial airliner cross the Atlantic on recycled cooking oil made sustainable aviation tangible rather than theoretical. The flight generated global media coverage that educated millions of people about sustainable fuel possibilities and created public pressure for faster adoption. But success also revealed the enormous challenges ahead. One flight using 70 tons of sustainable fuel consumed the output from thousands of restaurants over months of collection. Scaling this to handle millions of flights annually requires supply chain coordination and production capacity that currently doesn't exist. The gap between demonstration and implementation remains vast. Investment flows into sustainable aviation fuel production accelerated dramatically following Flight 100's success. Private equity firms, oil companies, and airlines committed billions of dollars to production capacity expansion and technology development. The successful demonstration eliminated much of the technical risk that had previously deterred large-scale investment in the sector. Airlines began negotiating long-term supply agreements to secure sustainable fuel access and manage price volatility. These contracts provide producers with revenue certainty needed to justify facility construction while giving airlines guaranteed fuel supplies for their sustainability commitments. The emergence of a forward contract market signals the maturation of sustainable aviation fuel from experimental technology to commercial commodity. The financial mechanics behind sustainable aviation fuel reveal why one successful flight couldn't immediately transform an entire industry. Airlines operate on razor-thin profit margins, where fuel costs represent nearly 30% of operational expenses. When sustainable fuel costs 4 times more than conventional jet fuel, the mathematics become brutal. A single transatlantic flight burning sustainable fuel costs an additional $200,000 in fuel expenses alone, money that gets passed to passengers through higher ticket prices or absorbed by airlines through reduced profitability. United Airlines CEO Scott Kirby captured the industry's dilemma when he estimated that scaling sustainable aviation fuel production to routine levels would cost $250 billion globally. That figure represents more than the annual revenue of the world's largest airlines combined. The investment requirement exceeds what any single company or even industry consortium can finance independently, demanding unprecedented coordination between governments, private investors, and aviation stakeholders. The economics become more complex when you examine regional variations in sustainable fuel availability and pricing. European refineries like Neste's Rotterdam facility produce sustainable fuel at costs that make it viable with government subsidies and carbon pricing mechanisms. But transporting that fuel to Asian or Latin American markets adds shipping costs that push prices even higher. Airlines operating international routes face the choice between paying premium prices for sustainable fuel or accepting the environmental and regulatory consequences of continued fossil fuel dependence. Carbon pricing systems create artificial markets that help bridge the cost gap between sustainable and conventional fuels. California's low-carbon fuel standard assigns credit values to sustainable aviation fuel based on life cycle carbon reductions, providing producers with additional revenue streams beyond direct fuel sales. These credits can represent 30 to 40% of total revenue for waste-based sustainable fuels, making production economically viable despite higher operational costs. The European Union's emissions trading system operates differently but achieves similar results by requiring airlines to purchase carbon allowances for their emissions. As allowance prices increase, airlines face growing financial pressure to adopt lower carbon fuels or pay escalating environmental costs. This regulatory pressure creates market demand for sustainable fuel independent of environmental motivations, driving commercial adoption through economic necessity rather than voluntary commitment. But regulatory systems also create perverse incentives that complicate sustainable fuel development. The preference for waste-based feedstocks over crop-based alternatives makes economic sense from a sustainability perspective, avoiding competition with food production and land use concerns. However, it artificially constrains the feedstock base and limits production scaling potential. The regulatory framework essentially caps sustainable fuel production at levels determined by waste generation rather than aviation fuel demand. Quality assurance challenges multiply as sustainable fuel production scales beyond small batch specialty operations. Each feedstock source requires different processing techniques and quality control procedures. Used cooking oil from European restaurants has different contamination profiles than waste oil from Asian food processing facilities. American municipal waste contains different organic compositions than European household garbage. These variations demand sophisticated quality management systems and flexible production processes. Fraud prevention becomes increasingly important as economic incentives create opportunities for supply chain manipulation. The premium prices paid for waste-based feedstocks motivate unscrupulous suppliers to mislabel virgin vegetable oils as waste cooking oil, capturing subsidies intended for genuine waste materials. Recent investigations uncovered extensive fraud networks shipping virgin palm oil from Southeast Asia, labeled as used cooking oil, undermining the environmental benefits that justify regulatory support. Authentication systems now require sophisticated chemical testing and chain of custody documentation to verify feedstock origins. Isotopic analysis can distinguish between virgin oils and genuinely used cooking oil based on chemical markers left by the cooking process. Blockchain-based tracking systems provide tamper-resistant records of oil collection, processing, and transportation. These verification measures add costs and complexity, but become essential for maintaining the integrity of sustainable fuel programs. The geographic mismatch between waste generation and fuel demand creates logistical challenges that mirror traditional petroleum supply chains. Major cooking oil waste sources concentrate in developed countries with established food service industries, while the fastest-growing aviation markets lie in Asia-Pacific regions with less developed waste collection infrastructure. This imbalance requires international shipping of raw materials or finished fuels, adding transportation costs and carbon emissions that reduce overall sustainability benefits. Storage infrastructure presents unique challenges for sustainable aviation fuel compared to conventional petroleum products. Many sustainable fuels have different freezing points, oxidation rates, and contamination sensitivities than traditional jet fuel. Airport fuel systems designed for conventional kerosene may require modifications to handle sustainable fuel blends safely. The costs of infrastructure upgrades get distributed across airlines, airports, and fuel suppliers in complex negotiations that slow adoption timelines. Seasonal variations in feedstock availability create supply chain planning challenges absent from petroleum-based fuel production. Restaurant waste oil generation fluctuates with tourism patterns, agricultural residues follow harvest cycles, and municipal waste composition changes with economic conditions. Sustainable fuel producers must either maintain expensive inventory buffers or accept production variability that complicates customer supply agreements. The technical complexity of processing diverse feedstocks pushes sustainable fuel production beyond traditional chemical engineering into advanced materials science. Converting municipal solid waste into jet fuel requires pyrolysis systems operating at extreme temperatures, followed by hydroprocessing under intense pressure and sophisticated catalyst management. The technology exists, but demands specialized expertise and equipment that few facilities currently possess. Research institutions worldwide compete to develop more efficient conversion technologies that can handle broader ranges of feedstock materials while reducing processing costs. Universities partner with oil companies and airlines to test innovative approaches including algae cultivation, synthetic biology, and electrochemical conversion processes. These research programs consume hundreds of millions of dollars annually while pursuing breakthrough technologies that could revolutionize sustainable fuel economics. Synthetic biology represents one of the most promising long-term approaches to sustainable aviation fuel production. Genetically engineered microorganisms can convert various organic waste streams directly into fuel precursor molecules, potentially eliminating complex chemical processing steps. Companies like Ginkgo Bioworks and Zymogen develop custom microbes designed to consume specific waste materials and excrete fuel components, creating biological refineries that operate at ambient temperatures and pressures. However, synthetic biology approaches face regulatory hurdles related to genetically modified organisms and environmental release concerns. The approval process for engineered microbes involves extensive safety testing and environmental impact assessments that can delay commercialization by years. Public acceptance of GMO-derived aviation fuel remains uncertain, potentially limiting market adoption even if technical and economic challenges get resolved. Electrochemical conversion technologies offer another pathway for transforming waste materials into sustainable aviation fuel. These processes use renewable electricity to drive chemical reactions that convert carbon dioxide, water, and organic waste into fuel molecules. The approach could theoretically operate anywhere with renewable energy access, eliminating geographic constraints imposed by feedstock availability or traditional refining infrastructure. The economics of electrochemical fuel production depend heavily on renewable electricity costs, which continue declining as solar and wind technologies improve. Current electricity-to-fuel conversion efficiencies remain too low for commercial viability, but research programs target efficiency improvements that could make the technology competitive within a decade. The ability to produce sustainable fuel directly from atmospheric carbon dioxide would eliminate feedstock constraints entirely while creating carbon-negative fuel production. Power-to-liquids technology combines electrochemical processes with traditional fuel synthesis to create sustainable aviation fuel from renewable electricity, water, and carbon dioxide. The process electrolyzes water to produce hydrogen, captures carbon dioxide from the atmosphere or industrial sources, then combines these inputs through Fischer-Tropsch synthesis to create hydrocarbon fuels chemically identical to conventional jet fuel. Several demonstration facilities operate power-to-liquids processes at pilot scale, proving technical feasibility while working to reduce costs and improve efficiency. The technology offers unlimited scaling potential since inputs come from abundant atmospheric sources rather than limited waste streams. However, current production costs exceed $10 per gallon, making commercial adoption impossible without dramatic cost reductions or massive government subsidies. The airline industry's approach to sustainable fuel adoption varies dramatically between carriers and geographic regions. European airlines face regulatory mandates that require minimum sustainable fuel percentages, creating compliance-driven demand regardless of cost considerations. American airlines operate in a more voluntary environment with tax incentives but no binding requirements, allowing market-based adoption decisions. Legacy carriers with extensive international networks face different challenges than low-cost domestic airlines in adopting sustainable fuels. International flights require fuel compatibility across multiple countries and regulatory jurisdictions, complicating fuel sourcing and certification processes. Domestic carriers can potentially source sustainable fuel from single suppliers and avoid international coordination challenges. Airline sustainability commitments create marketing advantages but also financial obligations that affect competitive positioning. Carriers that commit to ambitious sustainable fuel targets must either pay premium fuel costs or face public relations consequences for missing stated goals. This dynamic creates pressure for industry-wide coordination to avoid competitive disadvantages for early adopters. Fuel supply agreements between airlines and sustainable fuel producers increasingly include long-term contracts and volume commitments that provide both parties with planning certainty. Airlines secure future fuel supplies at predetermined prices, while producers obtain revenue guarantees that justify facility investments. These contracts often include price adjustment mechanisms tied to conventional fuel costs or carbon credit values. Airport infrastructure modifications required for sustainable fuel handling create coordination challenges between multiple stakeholders. Fuel storage systems, distribution pipelines, and refueling equipment may need upgrades to handle different fuel characteristics safely. The costs get distributed among airports, airlines, and fuel suppliers through complex agreements that can delay implementation timelines. Major airports increasingly market sustainable fuel availability as competitive advantages for attracting environmentally conscious airlines and passengers. San Francisco International, Los Angeles International, and Amsterdam Schiphol promote their sustainable fuel programs as differentiating features that support airline sustainability goals. This marketing approach creates network effects where fuel availability drives airline demand and vice versa. The insurance industry plays an overlooked but crucial role in sustainable aviation fuel adoption through coverage policies and risk assessments. Aviation insurers must evaluate whether sustainable fuels create additional operational risks that affect premium calculations. Successful operations like Flight 100 provide loss experience data that helps insurers refine their risk models and coverage terms. Manufacturers' warranties and service agreements also influence airline adoption decisions. Engine manufacturers like Pratt and Whitney explicitly warrant their products for sustainable fuel operation, eliminating concerns about voided coverage or increased maintenance costs. These warranties provide airlines with confidence that sustainable fuel adoption won't create unexpected financial liabilities. The certification process for new sustainable fuel pathways involves extensive coordination between fuel producers, engine manufacturers, aircraft manufacturers, and regulatory authorities. ASTM international standards committees evaluate each new production process and feedstock combination through rigorous testing protocols that can take years to complete. The approval timeline creates bottlenecks that limit the introduction of innovative, sustainable fuel technologies. International harmonization of sustainable fuel standards prevents the fragmentation that could complicate global aviation operations. The International Civil Aviation Organization coordinates standards development to ensure that fuel approved in one country meets safety requirements worldwide. This coordination prevents situations where airlines must carry different fuel types for different destinations. Military adoption of sustainable aviation fuel provides additional market demand and validation for civilian applications. The U.S. Air Force operates extensive sustainable fuel testing programs and has committed to significant purchase volumes that help justify production capacity investments. Military specifications often exceed civilian requirements, providing additional safety validation for commercial adoption. The geopolitical implications of sustainable aviation fuel extend beyond environmental benefits to include energy security considerations. Countries that develop domestic sustainable fuel production capabilities reduce dependence on petroleum imports and gain strategic advantages in aviation fuel supply chains. This national security dimension motivates government support for sustainable fuel development beyond environmental motivations. Trade policies increasingly recognize sustainable aviation fuel as strategic commodities deserving special treatment in international agreements. The European Union's border carbon adjustments will eventually apply to aviation fuels, creating trade advantages for low-carbon alternatives. These policies reshape global fuel trade patterns and provide additional economic incentives for sustainable fuel adoption. The workforce implications of sustainable fuel production create both opportunities and challenges for traditional petroleum industry workers. Many skills transfer directly from conventional refineries to sustainable fuel facilities, providing employment continuity for experienced workers. However, some specialized roles require retraining or different educational backgrounds, creating transition challenges for affected communities. Educational institutions develop specialized programs to train workers for sustainable fuel production and management roles. Universities offer degrees in renewable energy engineering, while community colleges provide technical training for plant operations and maintenance positions. These educational investments create the human capital necessary for industry scaling while supporting economic transitions in petroleum-dependent regions. Consumer awareness of sustainable aviation fuel remains limited despite growing environmental consciousness about air travel. Most passengers cannot identify which flights use sustainable fuel or understand the environmental benefits of different fuel types. Airlines struggle to communicate sustainable fuel adoption effectively while avoiding accusations of greenwashing or misleading marketing claims. The carbon accounting challenges associated with sustainable aviation fuel complicate corporate sustainability reporting and environmental claims. Life cycle emissions calculations vary significantly depending on feedstock sources, production processes, and transportation methods. Companies must navigate complex measurement methodologies while ensuring accurate and verifiable sustainability claims. Verification standards for sustainable fuel carbon reductions continue evolving as the industry gains experience with different production pathways and measurement techniques. Third-party certification programs provide independent validation of emissions reductions while standardizing measurement methodologies. These standards create confidence among buyers while preventing fraudulent environmental claims. The timing of sustainable aviation fuel adoption acceleration depends on multiple converging factors, including regulatory pressure, technological advancement, cost reduction, and public acceptance. Industry observers debate whether widespread adoption will occur gradually over decades or rapidly once key thresholds are crossed. The answer will largely determine aviation's ability to meet aggressive climate targets while maintaining growth in air travel demand. Flight 100's success demonstrated technical feasibility, but transforming that proof of concept into industry-wide adoption requires overcoming challenges that extend far beyond chemistry and engineering. The obstacles involve economics, regulation, supply chains, infrastructure, and human behavior. Success demands coordinated action across multiple industries, governments, and stakeholder groups in ways that few technological transitions have required. The complexity of this transformation becomes clear when you examine what happened in the months following Flight 100's success. Airlines around the world began requesting quotes for sustainable fuel supplies, only to discover that global production capacity couldn't meet even a fraction of their needs. The entire world's sustainable aviation fuel output for 2023 could power United Airlines' operations for exactly 11 days. Every other airline would have to wait. This supply bottleneck revealed the fundamental challenge that no amount of technical innovation could solve quickly. Building a sustainable fuel refinery takes 3 to 5 years from groundbreaking to first production. Each facility requires hundreds of millions in capital investment, specialized equipment that few manufacturers produce, and regulatory approvals that span multiple agencies and jurisdictions. The lead times for critical components like hydroprocessing reactors and distillation columns stretch 18 months, even when ordered from established suppliers. Meanwhile, the restaurant industry began experiencing an unexpected consequence of sustainable fuel demand. Used cooking oil that restaurants once paid to have hauled away suddenly became valuable enough that thieves started targeting grease dumpsters behind popular establishments. Police departments in major cities reported increases in grease theft as the commodity value of waste cooking oil climbed from 15 cents per gallon to over 80 cents per gallon in less than 2 years. Captain David Williams never intended to make history when he pushed the throttles forward on November 12, 2023. He was simply doing his job, flying passengers across the Atlantic using fuel that happened to come from restaurant fryers instead of oil wells. But his 8-hour flight proved that aviation's greatest breakthrough wasn't waiting in some laboratory or engineering facility. It was hiding behind every McDonald's in the world, getting thrown away by the gallon. Sometimes the most revolutionary solutions aren't the most complex ones. Sometimes they're so simple we've been discarding them every single day.